Me gusta la comida mexicana. I like Mexican food. And one of the things I like to do at Mexican restaurants is order a combination platter. And that's an important word for counting is combinations. And so we need to kind of pin down what that means. So let's say that we have a Mexican restaurant that has 5 things on the menu and like a truck, not a huge menu. So you have tacos and enchiladas and burritos and tamales and chili rellenos. And I decide to order 3 things. I'm going to order a taco, an enchilada, and a burrito. And my friend decides to order a burrito, an enchilada, and a taco. Well, we're going to get the same plate. So the order for a combination does not matter. So we have to take that into account when we count how many combinations there are. So we can start with this. If we have 5 items on the menu, then and let's say we're going to order 3. So what happens here is that you've got 5 choices for the first thing that you order. This is the same multiplicative rule we've been talking about. And then let's say there are no duplications, so you're going to have 4 choices for the second one. You can have a burrito, and now there are only 4 choices left. And you have 3 choices for the third one. So it looks like crudely there's 5 times 4 times 3, which happens to equal 60, but you're going to lose the pattern if you multiply it out. Don't multiply it out. Don't multiply it out. Anyway, 5 times 4 times 3. The problem is my plate and my friend's plate are the same plate, even though we made different choices as we went through this. So what we have to look at is how we're going to compensate for this. So what we have to worry about are the permutations. So that's the situation that we're in here. We've got combinations and permutations. I forgot to say that at the start. And permutation is ordering everything in a set. So if a set has 3 things in it, you get 3 choices for the first, get rid of that. 2 choices for the second, get rid of that. 1 choice for the third, get rid of that. So there are 3 times 2 times 1 permutations. You go all the way down to 1. And so if there are 4 choices for the first, then 3, then 2, then 1. And so the number of permutations of a set with n elements, that's where the order matters, is, well, there's a pretty fancy notation that works out really well. It's called n factorial. So the notation for that is an exclamation point. In England, they have much more fun with this because in England they call that a bang. So n bang, and by definition, that's the product of all the integers starting at n and going down to 1. N times n minus 1 times n minus 2 times 3 times 2 times 1. So that's how many permutations there are of a set with n elements. And if we go back now to the tacos, because I'm getting hungry, we can use this factorial notation to express what's going on with the situation. So remember, we had 5 choices for the first, 4 for the second, and 3 for the third. 5 times 4 times 3 is conveniently written this way, and this is going to look a little strange until you practice with it a little bit. It's 5 factorial over 2 factorial. And that, it must look a little strange. I'm sorry, it's over here. That must look a little strange. And so the way to think about that, and if you get stuck with factorials, the way that always works is start 5, 4, 3, 2, 1, and so forth. So we've got 5 times 4 times 3 times 2 times 1. Don't skip the 1. The 1's part of it. You won't get the pattern if you don't do the 1. And that was the top of this fraction. And the bottom is 2 factorial, which is 2 times 1. And what happens here is that you get this cancellation. So you've got the 1's cancel and the 2's cancel, and you're left with the 5 times 4 times 3. So what's happened is you've started down this path, 5 times 4 times 3 times 2, and you truncate it, and the easy way to express that mathematically is to divide out by what you've cut off. So that's the count, the raw count of the number of platters. But we've got to take into account the permutations. Taco, enchilada, burrito is the same plate as enchilada, burrito, taco. It's the same plate as burrito, taco, enchilada. There are 3 things that we've chosen here, and so that are the same. So we've counted everything that's possible 3 times. So what we get is we have to divide out by 3 factorial. So what we have is a fraction. The top is 5 factorial, and the bottom is 2 factorial times 3 factorial. So the 2 factorial comes from the choices that we didn't make, and the 3 factorial comes from the duplicate choices that we've made. And so the textbook calls this, they would call this P53. Oh, wait, I got that backwards. So you've got 5 is the number of things. There were 5 things on the menu. 3 was the number that we chose, and 2 was what we didn't choose. That was the leftover. No, wait. This is the same thing as, and this is an important property of these, P52. So the general formula is P and K is a fraction. The top is n factorial, and the bottom is k factorial, and then n minus k factorial. That's a product. So that's what we have here. If we have n is 2, if k is 2, then you get a 2 here, and the other factor on the bottom is 3 factorial. But if k is 3, then you get a 3 factorial here, and the other factor on the bottom is 2 factorial. So you end up with the same number, but you come to it different ways. And when counting, it's important to keep track of how you came to have a certain number. So there is the permutation formula. The combination formula, that's where the order matters, is C and K, and that's a fraction n factorial over n minus k factorial. So what I've done on the bottom here is generalize what I've done up here. Remember, I'm going to scan this and put it on Moodle so you don't have to worry about copying it down. Okay, so that's the story with combinations and permutations. The factorials can be a little tricky to work with. You have to really pay attention to what it is that it says. So I want to show you a couple of things that happen here with factorials. The one thing that you never, ever, ever, ever want to do is multiply out the various things on top. So if we have 40 things and we're going to pick 12, that's a thing that could happen in a more complicated system. The formula for that is it's a fraction. We'll have 40 factorial on top, and then 12 factorial times 28 factorial on the bottom. The 10 factorial is over 3 million, so you don't want to mess with 40 factorial because that's going to be 10 to the 30th, bigger than 10 to the 30th times 3 million. And so you can't really work effectively with this number. And you may have done a recursive program in your first programming course where you calculated factorials. And if you played with it long enough, you found out that you got something that was bigger than the machine word size. It's a gigantic number. You can't work with it that way. So what you need to do is to work, and this is already a gigantic number even as I've written it down, is you've got to work with the definition of factorial. And this is going to be a little bit tedious, but this is why we have computers. Anyway, 40 factorial is 40 times 39 times 38 times ... I'm going to put in some stuff in the middle and you'll see why I'm doing this. 29 times 28 times 27 times ... And then we're going to have 12 times 11 times 10 times dot, 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 times 3 times 2 times 1. So that's the top of the fraction with 40 factorial. The reason I picked out the 28 and the 12 is because those are going to be on the bottom, and let's see what happens. So first of all, on the bottom, we've got a 28 factorial. Oh, that's a gigantic number. But what we can do is I'm going to line them up like this. I've got 28 times 27 times times 12 times 11 times 10 times times 3 times 2 times 1. And our skins are saved because we have this massive amount of calculation. We've got 28 factorial on the bottom. That's 28 factors that match up with factors on the top, and so they cancel. So what we're left with now, oh, I'm sorry, I forgot there's also another factor of 12 factorial on the bottom. And so now what we're left with is 40 times 39, and we're going to go down to 29. Everything after 28 got canceled out. So 30 and 29, and then on the bottom we've got 12 times 11 times so forth and so on. Some people really enjoy this stuff. I don't know that there's anyone. Yes, I do know there's someone in this room. And now what you can do is do a lot of ad hoc stuff. So for example, you've got an 11 on the bottom here, and you've got a 33 up here. So those are going to cancel. So you can start doing a lot of cancellation and come up with a number. It's still a big number, but it's more likely that you can calculate it correctly if you keep in mind the meaning of factorial. So combinations, permutations, and the way we express those is factorials, and the way we compute those is not to compute the factorials, but to work with the expressions that we get. This is built into most calculators, and so these are important ways of counting. So we're counting one way if the order matters, and one way if the order doesn't matter. If the order doesn't matter, we have to divide out by the number of permutations of the set that you picked. So, bon appetit. I'm sorry, bon prosecco.